These are Algebra 2 notes, 6-5, graph cube root and cube root functions. This should be square root and cube root functions. I can't believe I never noticed that before. All right, so we are going to look at some new parent functions today. So the first parent functions we're going to look at are for square root and cube roots. So when we are graphing and it's an unfamiliar function, often we make a table. And we really want to think about what numbers we're going to put in for x. And so in this case, if I am going to take the square root of that number, I know that it does not make sense to put in any negatives. If I go to take the square root of a -4, it's not a real solution. I'm not going to be able to graph it. And so I don't want to do that. So the smallest number that I actually can square root is 0. The square root of 0 is 0. So I'm going to put a 0 in for x and then 0 in for y. I put a 1 in for x, square root of 1 is 1. And then I really want to think again. So do I want to use 2 in my table next? So if I put a 2 in for x, that means I have to take the square root of 2. And I know that that's going to be a decimal. And while I certainly can graph decimals, my goal is to make a quick, accurate graph. And if I don't have to work with decimals, then I'm not going to. And so I'm only going to pick numbers I can take the square root of. I'm going to pick perfect squares. So I'm going to put in a 4 for x and a 9. I'm just going to skip all the other numbers. 9 is the biggest one I can fit on this 10 by 10 x and y grid here. So square root of 4 is a 2, square root of 9 is a 3. And now I want to go ahead and graph. So I have a point at 0, 0, at 1, 1, 4, 2, and 9, 3. So the interesting part about this graph, if I flip it on its side, and I can't really do that and show you at the same time, but if you take this graph and you flip it on its side so that this is my y-axis up here instead, you're going to find that we really have half a parabola. I have that up 1 over 1, up 3 over 1, up 5 over 1 pattern. So I'm really like graphing that positive half of a parabola, which makes sense. If we think about inverses, with inverses we swap our x's and our y's, and a square root is an inverse of an x squared. So I hopefully that starts to make some connections in your brain and starts to make sense. So another way of graphing a square root function is just to start at a point that would be kind of like your vertex, and then just do that half of parabola with that 1, 3, 5, 7 pattern. Or you can do a table. I don't care either way, but the faster we get away from making tables is better. So on the second one, for a parent function for a cube root, I am going to have an XY table. Also, this time I want to think, can I take cube roots of negatives? And I can. A cube root of a negative number is just a negative. So I can take, for example, the cube root of negative 27, because a negative 3 times a negative 3 times a negative 3 makes a negative 27. So I do need to pick smaller numbers, though. I want to pick something that I can cube root. I want to pick perfect cubes, and I want them to be able to be graphed on here. So I'm going to choose negative 8, negative 1, 0, 1, and 8. So I was picking perfect cubes. So 1 is a perfect cube because 1 cubed equals 1. 8 is a perfect cube because 2 cubed equals 8. 3 is too big. It's not going to fit. So then I want to go through and take my cube roots. And then I'm going to go ahead and graph. So negative 8 for x, down 2 for y, negative 1, 0, 0, 1, 1, 8, 2. So it looks kind of like a cube graph, just again, it's on its side because my x's and y's are basically swapped because I'm doing an inverse. So then the next step, is I do have domain and range written down for both. And we can get our domain and range from the tables or from the graphs. I want to go through both. So one of the things I notice on this first graph is that it's all really, let me get a highlighter thing here instead to shade it in. It's really all in this quadrant 1. I don't have anything on the other side of the y-axis. I don't have anything below the x-axis. It's all in that positive first quadrant. So when I'm looking at my domain, if I'm just looking graphically, I can see that it's only on this x-axis, and it starts at 0 and it goes everywhere this way. So it goes from 0 up. And so that means that my domain is going to be x greater than or equal to 0. I can also see that on my table. My table doesn't have any negative numbers. It starts at 0 and it gets bigger. That's greater than or equal to 0. Now I want to think about my y-axis. My y-axis is going to be my range. So domain is your x's, range is your y's. D comes before R, X comes before Y. So for my range, I can see on my Y-axis that I start at 0, 0, and I go up along the Y-axis. I know it doesn't go very high, right? I'd have to have a really big graph to get it to go up to 10. The square root of 100 is 10, but I can tell that it can go in that positive Y direction. I'm just going to erase all this extra stuff now. And so my range is also going to be y greater than or equal to 0. I can also see that from the table. My table of values here for y starts with 0 and it goes up. And it can actually equal 0. I accidentally erased too much, erased my graph. On the next one, when I'm looking at my table, I have negative numbers, I have 0, I have positive numbers, which means my domain is all real numbers. And I can make that also with that fancy R, and I can tell all real numbers by looking at my graph. I have stuff over here where X is negative, I have 0, I have stuff over here with Y, with X being positive. So remember, when we're looking at our X axis, we're looking at that horizontal axis and trying to find where are we along that axis. When I look at my y's, I have negative numbers for y and 0 and positive numbers. So same thing, when I'm looking at my y-axis, I have stuff down here, I have 0, I have stuff up here. So my graph can stretch all the way along that y-axis. And so the range is going to be all real numbers as well. Which again is the fancy R. You can write one or the other, you don't have to write both. I just think for notes we write both. So here's our first one. We're going to graph y equals a negative 3 times the square root of x. So I want to think about how this graph compares with my parent function. And we've been talking about this stuff for a while. I know that the negative is what always reflects a graph. So I'm going to write reflected in the x-axis. And then I know that a number multiplied on the outside, like this 3, is going to be a vertical stretch. So vertical stretch by 3. So what I am going to do is I am just going to go ahead and do my normal graph. So I'm going to do 1, 3, 5. So I'm doing that pattern. And so this is like my half parabola. But then I want to do these changes. So I know that reflecting means instead of my point being up here, it'd be down here. But then I also need to multiply it by 3. So basically, I'm taking each of these y values. I'm not changing x, I'm only changing my y's. I'm taking each of my x values and I'm multiplying my x's by negative 3. So if this y is at 1, now it's going to be at negative 3. This y is at a positive 2, now it's going to be at a negative 6. And I am not changing my x values, right? My x is still 4, my x is still 1. So on this one, my x is 9, but instead of being up 3, it would be down at negative 9. So I've got my parent function and my new graph. So here's my new graph, and here's my parent function. So I multiplied it by a negative 3, and I flipped it. So basically all we had to do is we had to take our table. So this is for people that visually the graph is not making sense. I just had to take my table. So let's see, what's my original table? 0, 1, 4, 9, and then 0, 1, 2, 3. And I had to multiply my y's by a negative 3. That's all I have to do. So my domain here is interesting. My domain, now my graph is only in this region down here. So my x's are still positive, right? I'm still on this positive x-axis. So I'm still over here. So my domain is still x greater than or equal to 0. But because I flipped that graph below my x-axis, now I'm only into all those negatives for y. So my y is going to be less than or equal to 0. So you could definitely make a table for this if you're not comfortable. You could have this middle row for square roots. You could make one more row for negative 3 times that number, and you could go ahead and graph that instead. But we really want to get to the point where we can look at some of these graphs. We don't have to do a lot of work for a table, and we can make a graph right away. Our goal is always quickly sketching these graphs so that we can get information from them. On the next one, we're going to take our cube root and multiply it by a half. So we know that's going to be a vertical shrink by a half. And all we're really doing is we're multiplying our y's by 1/2. So you could make a table or not make a table. I kind of already know my perfect cubes. So the cube root of 1 is 1. The cube root of 8 is 2. And I'm just going to kind of mirror that on the other side with our negatives. So that gives my original graph. This one's going to be harder to see. 1/2 is going to be kind of tricky. So this is the cube root of x. But then if I am vertically shrinking this, all of my y's are being multiplied by 1/2 or divided by 2. So instead of having a point at 2, it's going to be at 1. Instead of having a point at 1, it's going to be at 1/2. So I am just kind of shrinking that down. And maybe this is one where you don't actually draw the original graph. Maybe this is one where you just plot some points from the parent function and then do your graph that looks like it's been smashed. But it really should look like it's vertically smashed or vertically compressed. So there is my final graph, 1/2 times the cube root of x. So that's going to be right here. So my domain, my graph still stretches all the way across my x-axis. I still have negative y's and positive y's. So I have all real numbers for both. Doing the cube roots is a lot easier. So we have some information here about graphing radical functions. And just like before with parabolas, if I have a minus h and a plus k, that means that it's going to move h units and k units. So it would go like up and right. As if those are positive, it's always opposite sign and then the same sign, just like parabolas are. Same thing here. So the important steps to remember when we're graphing is we're always stretching and shrinking first, and then we're shifting. So for this first one, I would probably, let's see. First of all, let's write down what we're doing. We're doing sorry about that. We're doing a vertical stretch by 2, and that's what we would do first. And then because it says plus 3 minus 1, we're really moving it 3 left. And this is a translation, and 1 unit down. So because of this 2 right here that's being multiplied outside of that square root, I have a vertical stretch by 3 because it says a plus 3 in my x direction because that's affecting x. It's inside. X is always the inverse of what it says. It's not really moving positive 3 units for x. It's moving 3 to the left instead. The number outside is always like a y-intercept kind of a thing, and so I'm moving 1 down. So in order to graph this, first I'm just going to worry about graphing that 2 times the square root of x. So I'm going to figure out the square root of x. I'm going to figure out 2 times the square root of x. I could do this all on my graph, but this is a lot of changes, so I think this is going to be easiest for me. So my x numbers that I want to square root are 0, 1, 4, 9. So first I'm going to take my square roots, and then I'm going to multiply all of those by 2. So this would be 0, 2, let's see, 2 times 2 is 4, 3 times 2 is 6. So these are going to be my x's, and these are going to be my y's that I graph. And then after I graph this, then I'm going to shift it. Okay? So it's really important that we do the multiplying first and then the shifting part. So let's go ahead and graph this. So I have a 0, 0 still, but instead of doing 1, 1, now I go 1, 2 because I'm multiplying my y's by 2. And then I'd go over to 4, but instead of up to 2, now I'm up to 4 because I'm multiplying it by 2. And then I go to 9, and then instead of up 3, it's now up 6. So there's my new graph. This is for 2 times my square root of x, but then I have to shift it. So I'm going to shift each of my points. I'm going to count 3 left and 1 down. So 1, 2, 3, 1 down, 1, 2, 3, 1 down, 1, 2, 3, 1 down, 1, 2, 3, 1 down. And so here is my new graph. It really shouldn't be going down at the end. It should look like it's going up. So this is my y equals 2 times the square root of x plus 3 minus 1. So there's our parent function. Well, it's not really a parent function, but there's the function where we've just vertically stretched it, and then there's our shifted one. Our domain this time is really interesting. So my domain, I can see that my graph is now in this region. So because I've shifted it, it's not just going to be greater than 0 this time, is it? So this time, my point, this part of my graph, this point is at -3, -1. And so my x's start at -3 and then get bigger. So domain is x greater than or equal to -3. My range, let's see, my y's start at -1 and go up. So my y is greater than or equal to -1. So we've got one last graph we're going to try out. It's another cube root. So first, and let's see, we're reflecting it in the x-axis. Let's see, that 3 on the outside of the square root means we have a vertical stretch by 3. And then we're translating again, and we are going to translate, let's see, it says x minus 4, and that's affecting my x because it's inside my root with the x. So that's going to be the inverse. So it's going to be 4 to the right. And then it says a plus 2, so that I'm going to go up 2. So I'm going to just start out by making a table. I want to list all those x's that I would normally square root, or sorry, normally cube root. So -8, -1, 0, 1, 8. And I'm going to find the cube root of them really fast. But then what I really want to do is multiply those by -3. And then once I make that graph, I'm going to shift it. So I could make 3 different graphs here, but it's going to be really confusing if I had that. I don't want to make my original parent function and then stretch it and then translate it because it's just too much. So let me go through and do the cube roots. So cube root of -8 is -2. This is a -1, 0, 1, 2. And then I really want to take these cube roots and I want to multiply by -3, right? I'm always changing my y values. So my x is going to be the same, but I want to multiply my y's by -3. So I'm going to look in this middle row and I'm going to multiply all those y's by -3. So -3 times -2 is a +6. -3 times -1 is a +3. -3 times 0 is 0. -3 times 1, -3. -3 times 2, -6. So when I graph this, I'm not going to graph that middle row. I am going to graph just the negative cube root of -3 times the cube root of x. So let's go ahead and graph our x's and y's. So -8, 6 is going to be here. -1, 3, 0, 0, 1, 3, and then 8, -6. So here's my cube root. Kind of ugly the way I'm connecting it. It's a little bit tricky drawing on the screen sometimes. So this is the negative cube root, -3 times the cube root of x. And then I want to do my shifting. So I'm going to shift all of my points 4 units to the right and up 2. So I'm just going to take each point and count 1, 2, 3, 4, up 2, 1, 2, 3, 4, up 2. So it's really cool to me in math that it doesn't matter what kind of function we're looking at. They all kind of follow these same rules. And it's really exciting that we can just come up with a parent function and learn some things and then apply that on every single graph we do. It's pretty amazing that once you learn something like that, you can apply it everywhere. So this is the end of our 6-5 notes.